All right, let's go ahead and get started. Welcome to day 8 of Organometallics. Hope everybody enjoyed the guest lecture from Josh Figueroa on day 7. We'll pick up where we left off last time, which was wrapping up the day 3 or the third installment of the elementary steps / elementary reactions portion of the class. So just to situate everybody in terms of where we are in the syllabus as we lead up to the midterm, we're wrapping up elementary steps here, a few additional notes, then we'll jump into metallocarbenes and then move forward to catalysis, ligand design, and then ultimately case studies of individual catalytic reactions that are of high importance. So in the lecture from last time, we ended with a discussion of 1,1 migratory insertion that is most common with carbonyl ligands, but also relevant to carbenes, which serves as a appetizer for today's lecture. So there are 2 forms and flavors of migratory insertion, the first being 1,1 migratory insertion, and the second being 1,2 migratory insertion that is commonly observed with alkenes, alkynes, and related pi systems. Carbonyls, amine, for example. So we'll cover this 1,2 migratory insertion now and its microscopic reverse, which would be beta elimination. So 1,1 migratory insertion is the yin to the yang of alpha elimination, and 1,2 migratory insertion is the yin to the yang of beta elimination. So in terms of general schematic here, in the 1,1 migratory insertion, we're going to have a bound, typically diatomic, well, not necessarily diatomic, but typically a bound pi system coordinating through a sigma bond, and then a coordinated ligand, something like a hydride, a carbogenic group, or in some cases heteroatom substituents will migrate into the bound pi system. It will open a new coordination site and then form one new sigma bond. So you can already from this get a sense of the thermodynamics, the thermodynamic considerations at play. We're swapping, let's say we have a alkyl ligand, then we're swapping this MR bond for a new metal alkyl. We're trading that bound olefin ligand for whatever the new capping ligand is going to be. And so there's a thermodynamic consideration here and a kinetic consideration in terms of the migratory aptitude, and we'll talk about that. Just as a little bit of trivia to get us warmed up today, does anybody want to take a stab at a molecule, and there could be more than one here, but what molecule or molecules can undergo both 1,1 and 1,2 migratory insertion? It has to have a special set of properties since it needs to have a pi bond, but also needs to be able to have this kind of amphiphilic character at the coordinating group. So it's one that we talked about briefly, which is SO2. And I won't say too much more about that because it's relatively uncommon, but you can think about those 2 mechanisms. Okay, so there's some nomenclature here that's worth commenting on. So depending on what the migrating group is, let's say it's a hydride, this process will sometimes be referred to in the literature as hydrometallation. If it's a carbogenic substituent, an aryl or alkyl, it's sometimes referred to as carbometallation. These processes, I would say, in general, are They're both a subset of migratory insertion, but they're also in some ways less specific mechanistically. So sometimes people will refer to a radical addition with concomitant formation of a carbon metal bond as a carbometallation, even though there's not a formal migratory insertion involved. So the nomenclature here gets a little bit murky under the boundary conditions or at the boundary conditions. But first approximation for what we're talking about in today's lecture, you can think if that's a hydride, hydrometallation, it's a carbogenic group carbometallation. And likewise, if it's a nitrogen substituent, aminometallation, and so on and so forth. So let's walk through this this step here with hydride as a representative case study. So initially, we're going to coordinate the metal hydride to the olefin. And then what will take place moving left to right on the screen is formation of a new carbon H bond and a new carbon metal bond. That the newly formed CH bond can then reach around and form a stabilizing dative interaction that we're referred to as an agnostic interaction. We'll comment more on this in a moment. And this is a free center two electron type of bonding interaction, not dissimilar to things we've seen before, like sigma complex. This is effectively a tethered sigma complex, agnostic interaction. And then pushing this forward, we then have a trapping ligand L that will come and coordinate and occupy the vacant coordination site that was made available here. And in many cases, this will provide the thermodynamic driving force or contribute to providing thermodynamic driving force for the overall forward reaction. The process is syn stereospecific, as you can appreciate from the mechanism, at least in the classical 1,2 migratory insertion. Reactivity trends here, there are some similarities, but also some notable differences in terms of 1,1 versus 1,2 migratory insertion. So like 1,1 migratory insertion, in 1,2 migratory insertion, one needs to consider both thermodynamic and kinetic factors. But in general, one way to think of it is that you're in a 1,2 migratory insertion, you're not starting in as deep of a thermodynamic well. So you typically have a broader range of migrating groups that are thermodynamically allowable in terms of migration. So what does that mean? We heard that in a 1,1 migratory insertion, hydrides do not migrate except under very, very specialized circumstances, but in a 1,2 migratory insertion, those are very much in play, as you just saw from this case study of a hydrometallation. And then, so those migrate most quickly, followed by metal alkyls and metal aryls. They will also migrate. I think in some literature, you'll hear that these don't migrate well or migrate more rarely, but I think at least in my lived experience, that's not necessarily true, because we know that this is a constituent elementary step of the Mizrachi-Heck coupling, and but it is less facile certainly than corresponding hydro or alkylative processes. And so there's the kinetic component of that is, the hybridization of the migrating substituent, this level of steric encumbrance and steric clashing. So you can imagine hydrides exhibit the least steric clashing, and then alkyls exhibit a fair amount of steric clashing, but have more conformational flexibility, and aryls experience more steric clashing upon migratory insertion. And then there's also the thermodynamics, which is the strength of the bond that you're breaking versus the strength of the bond that you're making. So metal hydrogen bonds, as we saw, are relatively strong compared to metal alkyls, which are weak, and then metal aryls are kind of in between. So they're stronger than a metal alkyl because of this back bonding component, but then weaker than a metal. Right. Okay, so let's touch more on this. Actually, let's finish one more set of notes here. So again, carrying forward with our case study of hydrometallation, let's talk about the regioselectivity considerations. And the preferred regiochemical outcome in a hydrometallation depends on several factors, but one that plays a dominant role is what type, the type of olefin in question, and whether it's conjugated, non-conjugated, strained, unstrained, substituted, unsubstituted, et cetera. So let's consider three limiting scenarios. So the first would be like a styrenol type olefin, a conjugated olefin. So here the preferred regiochemical outcome places the CH at the terminal position and the metal in the benzylic position. Why is that? There's two contributors. One is that when the metal is in the benzylic position here, you have the advantage of this haptotropic stabilization that we talked about, where it could be the eta-1 benzyl or the eta-3 benzyl. That's a stabilizing interaction. And then another important consideration that I think as organometallic chemists, we should always have in the back of our mind, but sometimes don't, is in this type of migratory insertion, it's insufficient to only consider the new carbon metal bond that you're forming, but also the new CH bond, or in the case of carbometallation, the new CC bond that you're forming. And you see here that compared to the alternative regiochemical outcome where you would form a CH bond at the benzylic position, you form a homobenzylic CH bond that is relatively strong. So you have two points that argue in the same direction in terms of favoring this regiochemical outcome. We can consider conjugated alkenes like acrylates, vinyl ketones, et cetera. And first approximation, the analysis is similar. When we have a metal when we place a metal at the alpha position, let's draw this out in the case of an enone. You all know from your experience in main group chemistry that what you've really generated here is an enolate. So this is the C-bound form, and then you also have the potential for the O-bound form. And similar to haptotropic stabilization, this provides a means of stabilizing intermediate that's formed. In favoring this beta addition pathway. We can also consider the case of simple alpha olefins, i.e. alkyl substituted terminal olefins. And in this case, these will typically proceed with so-called anti-Markovnikov regioselectivity, where the CH bond is formed at the internal alkenyl carbon atom and the carbon metal bond is formed at the terminal position. Why? In this case, there's a major steric component. The metal, remember, is big, and the metal prefers energetically to be at the least hindered position. Okay, questions on those regioselectivity trends? Yes, Rika.
If R was like a heteroatom, would it be the same selectivity as R equals phen?
If R was a heteroatom, would it be the same as R equals phenyl? And that's a good question. I think I don't want to make an overly general statement. I would say it depends. It depends. But I think if your intuition is that it's more similar to a styrenyl system than an alpha olefin uh, is on point. But I wouldn't feel comfortable overly generalizing to say it always goes that way. And what I have in mind here is like, let's consider a case study of a vinyl ether versus a vinyl acetate. Well, then already you can see there's going to be a major difference, because in the vinyl acetate case, you've got this potential for chelation stabilization of the carbonyl of the acetate. In a simple vinyl ether, you wouldn't. Let's say you have a difference between a silyl version of the vinyl ether, so a silyl enol ether. That silyl group could be very bulky. So you have a TMS or TIPS group there, then you have an added steric component. So that's why I'm cautious to overly generalize, because each heteroatom is going to have different flavor to it. Yes.
Where you have the O bound versus C bound drawn.
Yeah.
Should that double bond be in a different?
Thank you for catching that. Yeah. Thank you, Amy. Okay, so let's now go back to that point I made about agostic interactions, and we'll linger on that for a moment. So what do we mean by agostic interaction? Where does this funny term come from? And that brings us to our day 6 chemist of the day. I don't know if anybody recognizes this individual. Everyone's avoiding eye contact, so maybe not.
He's in Alabama. Oh, wait, no,
That's day 8. Yeah,
that's all I can say. Is the license. I'm sorry.
that's good. I appreciate the attention to detail. Any takers for day 6? We have a name that'll come up several times in the context of today's lecture, Maurice Brookhart, of formerly of University of North Carolina, Chapel Hill, now at Houston. He's famous for, among other contributions, coining the term agostic interaction together with collaborator Malcolm Green, developing a series of widely used polymerization catalysts, so-called post-metallocene catalysts that we'll cover today, and a number of other contributions. There's a really nice biographical write-up of him in Organometallics that I've included as readings if you're interested in hearing more about his career. But the key point for the context of this discussion of agostic interaction is that in considering the crystal structures of complexes of this general type, so let's just do a quick electron accounting exercise of this titanium complex. So what do we have here? First, oxidation state of titanium. Anyone quickly? Titanium +4. Which is D what?
0.
0. How many ligands do we have around? 1, 2, 3, 4, 5, 6. Okay, we're going to have 12 electrons. No D0, so overall electron count is 12 electrons. Okay, so right off the bat, we are oriented that this is a very electron poor flavor of a metal. I think Josh, in Josh Figueroa's lecture, he made this analogy, which resonated with me, of parallels with the main group versus the transition metal series. When you have 6 electron carbon, i.e. a methyl cation, you can appreciate the level of instability that has, and that there are some parallels there when you talk about very low electron count metal centers. So this is not happy. It does not have enough electron density. And so in that case, what can happen? Well, you have this tethered ethyl group. And so from this tethered ethyl group, the metal wants to find electron density anywhere it can get it. And it's willing to even dance with a CH bond. And so just as an exercise, we can consider this Now, you saw that when we do electron counting in sigma complexes, if we just consider that a full dative ligand, then everything that we did previously stays the same. It's just that now instead of 6 ligands, we have 7. So then our overall electron count is going to be what? 14. So it gives you a sense of that it's getting closer to that preferred 18 electron state. It's not perfect. But these kinds of interactions were a point of great curiosity to Brookhart and Malcolm Green and the broader community. We can see how this manifests in the X-ray crystal structure, and the key angle that they were looking at. Remember that in an X-ray crystal structure, H atoms are difficult to position because hydrogen atoms do not diffract X-rays strongly. To precisely position H atoms, you typically need to rely on single crystal neutron diffraction. So the key parameter that they were paying close attention to is this unusually acute angle here. And they came up with this descriptor. And of course, you can now see this connection to the beta hydride elimination step, because this titanium H bond doesn't know if it's breaking or forming. It's kind of caught in this intermediate state. They came up with this term, agostic interaction, from a Greek term that literally translates to holds close to oneself as if like a shield. And why they came up with this strange term, well, there are a lot of strange terms in organometallic chemistry, but in this case, Brookhart was at a sabbatical, the story goes, at Oxford. And so you can imagine at Oxford, you sit around funny tables like in Harry Potter and wear capes and talk about strange things. And so they were sharing these observations and struggling with the terminology at dinner and having a conversation with a scholar of ancient Greek who suggested this obscure term of agostic interaction. And another fun fact is that if you type agostic interaction in Word, it will autocorrect to agnostic. So that's something to watch out for. It's not an agnostic interaction. Okay, so let's take a look at a modern example from the literature of an agostic interaction. Here's an example from Allison Fout's group at Texas A&M. And Allison's group has been interested in first row metal complexes and supporting ligands for various types of catalysis, and documented this interesting example of a agostic interaction of a CCC pincer ligated iron mesotile complex. And so one question I'd pose to you is what are the diagnostic features of an agostic interaction? We talked about X-ray and neutron diffraction. But if I wanted to convince you as the referee, or you wanted to convince me as the author, and I'm the referee, that there's an agostic interaction, what analytical techniques do you think would be convincing? Take volunteers here. Here says proton shift in what spectroscopic technique? Proton NMR, okay? And what do you expect to see in the 1H NMR? Would it be upfield of normal, downfield of normal?
It's closer to the metal center of your field. So, I don't know.
Okay. You might not know off the top of your head. You know it would be different, so you'd have some chemical shift. And in this case, they see an upfield shift. That makes sense because some of you may know that where do metal hydrides typically show up in the NMR? Negative. They're so far upfield, they're actually negative. And so an agostic interaction is part of the way on the road to becoming a hydride, potentially, or it thinks it is. So it shifts upfield. That's what they see. Great. What else might you expect to see in the proton NMR besides that shift? If that bonding interaction is strong enough that rotation about this CC axis is slow on the NMR timescale, you might expect to see now many of the protons in this mesotyle becoming inequivalent. So from just a symmetry perspective, actually both methyls should be the same and all of the CHs on those methyls should be the same. But if rotation is slow, you'll see symmetry breaking. So these two, all three of these CH will be inequivalent. No, these two can still be equivalent. This one will be different. Any other techniques off the top of your head? Think about.
If complex is amenable to an EPR, you might be able to see that there's an interaction between the metals.
EPR, okay, that's interesting. Potentially. I think you would need, in that case, you'd probably need some reference to know what you're looking. IR potentially, but remember that CH region where you're going to be looking is the noisy one, so there's a link between them.
Maybe one thing you could do is you could try to synthesize similar complexes where the mesotyl protons either don't exist or there's something else there that's incapable of doing those interactions. And then provided that it's still symmetrical, you could say, well, this one doesn't experience symmetry breaking or something like that. Maybe you could also make a similar, like an iron complex that has a similar electron count, and then compare the reactivities and benchmark it to different iron complexes and say, well, this is in the same territory as, so it wants to,
Yeah, I like what you're thinking about. I'll just broadly categorize that as synthetic analogs, and then depending on what you are testing, they might design, the design might be a little bit different. Cool. And so here, if you want to read more, I think NMR turned out to be the diagnostic in the actual study. NMR turned out to be the Neil McLaughlin. You can read more about it in this ChemCom 2022 paper. All right, let's see now some migratory insertions in action in the context of catalysis. And this will actually be in the context of catalysis as applied to material synthesis. So let's consider this interesting zirconium bis-CP methyl cationic complex. And you might appreciate that that doesn't look super stable. Where did that open coordination site come from? We'll talk about that in a moment. And we're going to expose this to ethylene. The first step will be that ethylene binds to the open coordination site, still cationic because ethylene is an L-type ligand. What will happen next here? Oliver, what do you like?
Will it do the insertion and you'll get the ethyl side chain with a high zirconium high?
Beautiful. Okay. So we now have open coordination site here. Methyl is inserting one, two, three, CH3. We'll just color code that so it's straightforward to track. All right, and we're still under this positive atmosphere of ethylene. So what do we think now?
Just get another one that comes in and coordinates.
Another one. And ad infinitum, and so on and so forth, until you get to what in the end? Polyethylene. And this process has a name, the broad category of this coordination-based polymerization with early transition metals. Does anybody know off the top of
Ziegler,
Ziegler-Natta polymerization? Great. Named after the German chemist Carl Ziegler and the Italian chemist Natta. Natta extended Ziegler's system to polypropylene synthesis. And I think I don't remember the exact numbers. It's something like performed on, there's some variations of it. different initiator systems, heterogeneous versus homogeneous, was producing something like 100 million tons of polyethylene every year and was pretty much the world's sole source of polyethylene pre-1990s. Of course, this was a Nobel Prize winning discovery, and the patents from this were part of the fuel that have propelled the Max Planck Institute for Full Enforcement, the COFO, for many years since initial discovery. When I was an intern at a postback at the MPI, the COFO, I walked by Carl Ziegler's Nobel Prize every day on the way to lunch. So that was a great source of organometallic inspiration. Okay, so I mentioned something changed in the 1990s that made that came online and complemented Ziegler-Natta polymerization. So what is it? So let's consider now this system, so-called post-metallocene system, from who else but our chemist of the day, Maurice Brookhart. So what's going to happen here? We have dimethyl nickel bis-imine complex, and then we're going to treat it with this unusual looking Bronsted acid. What's going to happen here? Think back to our how to enhance ligand exchange. Al, what do you think?
Loss of methane.
Loss of methane. Gas, that'll come off, and now you have your open coordination site. In an ethereal solvent, this will actually coordinate ether. And as it turns out, in this particular case, this is a stable isolable complex. So we talked about, in the context of this Ziegler-Natta metallocene polymerization system, open coordination sites. How do you open them? This is one way to do that. As it turns out, this interesting looking acid has a name also. Al, do you happen to know this one?
No, sorry.
Any takers? Well, if we stay with our chemist of the day theme,
Cards acid.
Brookhart's acid. True Renaissance man. So what are the special properties of Brookhart's acid? Why does it get a name in the context of organometallic chemistry? It is the canonical example of an H+ in association with a WCA, a weakly coordinating anion, in this case, BARF. What is BARF? BARF is this weakly coordinating anion, means that it does not, there's no site of high enough electron density to really stably coordinate to the metal, so it stays outer sphere. So if you want to encourage formation of cationic complexes to increase their reactivity, this is the way. It's one tool associated with a weakly coordinating anion that isn't going to quench that cationic character, and BARF is a popular one. Okay, so we've taken our pre-catalyst, we've activated it with Brookhart's acid, we have the cationic form, now we're coordinating ethylene, and what we see is similar to what we saw above. Iterative processes of migratory insertion, coordination of ethylene, migratory insertion again. So we can play this script forward and just get to linear polyethylene, but we can also, at this point, appreciate that upon growth of the polymer chain, we have this tempting looking CH bond at the beta position. We had just said that this can form an agostic interaction, and an agostic interaction can lead us down the road of beta hydride elimination. If that happens, that gets us to a hydride, nickel hydride bound to the olefin. And now you have a couple choices. Either it would just undergo the reverse of what just happened and get you back to this linear growing alkyl metal polymer chain. Or alternatively, the polymer can be lost as a alkene terminated polymer through associative ligand exchange, another molecule of ethylene. Remember, we're under atmosphere of ethylene, so you have a large excess that can come in, displace, and that's a chain transfer event. That process you can control, try to slow it down through bulky ligands that prevent associative ligand exchange, application of some of the concepts we've discussed already. Or alternatively, this can reinsert, but wrong way around. And now what happens is you start to introduce branching onto your polymer chain. And in fact, this ratio of linear to branch that you get out is directly a consequence of the reaction conditions as well as the properties of the ligand. And so this allows you to tune between high density polyethylene, ultra high density polyethylene, low density polyethylene. And I think all of these different materials you have encountered and probably already today. And the key point here, why do people go to trouble of making and characterizing and studying these post-metallocene complexes is that you have now a different ligand set. You're in the late transition metal part of the periodic table. You've got a different ligand set. You've got different ways by which you can tune. Of course, going late transition metal, you have less sensitivity to moisture and air. This was a big breakthrough, the discovery of these so-called post-metallocene polymerization catalysts. All right, any questions on that? We'll go rapid fire through this next part because it's just running that previous script in reverse. We talked about hydrometallation. The microscopic reverse of that is beta hydride elimination. We just saw how that can manifest itself in catalysis. What makes beta hydride elimination favorable? It becomes favorable if there's an empty orbital cis to the alkyl ligand that favors formation of that initial augostic interaction en route to CH bond breaking. And if you know that's the case and you then want to suppress beta hydride elimination, let's say you're trying to do a challenging alkyl-alkyl or alkyl-aryl coupling and you're struggling with getting mixtures of linear to branched, how could you suppress beta hydride elimination? Adding trapping ligand or adding excess of your ligand to close any potentially open coordination sites is a documented effective strategy. Here's an example, early example from Paul Wender's group where they use this to great effect. Beta hydride elimination, again, this is a direct consequence of what we already covered. Beta hydride elimination is typically more facile than is beta alkyl elimination, just like that's a consequence of the fact that these are microscopic reverses of the migratory insertions. And that should be reassuring somewhat, because then if you think back to like this example of a propagating polymer chain, you can imagine how complicated this gets if not only are you fighting beta hydride elimination, but the polymer is actually like chewing itself up through carbon-carbon scission as you're trying to stitch it together. In some cases, you have an interesting competition that merits discussion, and that is between beta hydride elimination and beta heteroatom elimination. So this can take place, we'll cover as an element, as an example of homogeneous catalysis, the Walker oxidation, where you have initial oxymetallation, and then that thus generated alkyl metal reacts via beta hydride elimination, but alternatively, it can react via the microscopic reverse of what just happened, and it can undergo beta heteroatom elimination. And the selectivity rules, the selection rules for whether beta hydride or beta heteroatom elimination were not really well understood until somewhat recently. A really nice study from Bill Morandi's group here from just a couple of years ago came online and demonstrated that it's a combination of factors like the steric and electronic properties of the ligand, as you might expect, the nature of the leaving group. So I'll direct folks to this reference if you want to read more about that. Somewhat specialized case, but you may encounter something like this in the context of your research. For example, if you're doing a Heck reaction on some kind of nucleoside precursor, it's not uncommon that you have situations where you have competing beta H versus beta acetate elimination pathways that are accessible. Okay, let's now consider another example. This will be this is a classical one. So we're going to do some work with this interesting zirconium hydride complex, whose name is, anyone want to throw it out there? Schwartz's reagent, good. Spell that correctly, Schwartz. Okay, synthesis of Schwartz reagent. Give me some thoughts here, Eyal. How would you make this?
Carbenes dichloride and reductant.
I think I heard zirconium dichloride. Why do you like that as a starting material? Cheap, stable, probably not gonna decompose in the air. All right, so then you said treat with a hydride. What hydride source do you like? Dibol, okay. We're going forcing aggressive metal hydride. And that is indeed how you can make Schwartz reagent, but what might happen if you do this and take a really forcing hydride is that you might get Schwartz reagent in combination with the common byproduct, which is what would be, I think I heard somebody whisper it,
Double hydrogen.
dihydride, okay. And these will have different reactivity profiles, so that might be a complicating factor.
If you run the reaction in THF, the dihydrogen falls out much more easily than water.
Okay, and then if you wanted to convert dihydride to monohydride, you can treat with, I can draw it, DCM. All right, that got a little tight. Let me redraw that so it's clear on the notes. Okay, good. All right, so we've got our Schwartz reagent in hand. We're going to treat with this internal Z olefin. This is not the most interesting reaction in the world, but we'll see the point I'm trying to make here. Yeah, what happens next? So olefin coordinates. Now what do you have?
You have a migrating insertion.
Migratory insertion. Okay, hydride's going to migrate in here. Tell me something about the stereochemistry that we will observe. Yeah,
Cis.
okay, syn addition. And then what will happen next? Stop here. Use it in the reaction. What happens next?
That beta hydride.
So if it beta hydride eliminates, you could, that would be reasonable, then that would go back here. Right?
I mean, there's a easy isomerization.
Easy isomerization. Okay, so that is one thing that could happen. You could potentially eliminate the other CH bond, and then that would lead to easy isomerization there. What else could happen? That would be, you know, roughly thermodynamically neutral, a little bit down. That would give you a little bit in energy potentially. But if you want to get all the way thermodynamically downhill, what would need to happen? Is the zirconium happy in its secondary alkyl position?
No.
No. Where does it want to get from a thermodynamic perspective? Ningxi, what do you think?
Will it migrate to the primary position?
Okay, give me some elementary steps for how it's going to migrate to the terminal position.
It will do beta hydride elimination.
with the primary methyl proton.
Aha, okay.
You
so
got,
We're gonna have here, first step, which is implicit, sometimes not drawn, is we're gonna have a bond rotation. We'll draw that out just so it's clear why this is not, oops, why this is not just the microscopic reverse of what we just had. So we have a bond rotation. I realize this is kind of a painstaking detail, but I think sometimes these details are important. So we've rotated the ethyl out of the way. And now we've got the methyl that is accessible. So you said you're going to beta hydride eliminate from here. That gives you something inequivalent from, so sorry, let me draw this out here with this open coordination site so that it's really clear. And then now you're going to have a bound terminal olefin hydride, and I think if I heard you right, Ningxi, you said this is going to react further to make a primary alkyl zirconium species. Is that correct? One, two, three, four. And this process is called chain walking. Which generally refers to the phenomenon by which alkyl metal species will migrate up and down an alkyl chain and find its thermodynamic happy place. It could be a benzoic position. If there is an accessible benzoic position, it could be a terminal position. If it's a terminal position. Questions on that? Okay, let's see another example now. This is problem of the day number 3 from the day 6 problem set, but we're going to combine a couple of the elementary steps we've learned here. So if you don't have the day 6 worksheet, I think both day 6 and day 8 are up here, but I've just redrawn this here, so you don't even necessarily need to look back at it. Take 30 seconds to think about this. We're going to treat this interesting P pi P palladium complex. The first thing you can think through is what's the oxidation state of this palladium complex? What's its electron count? Let's start building a predictive framework for how it might react. And then we're going to treat it with HCl. Step 1, heat it up. Step 2. All right, Nima, what do you think? Get us started here. First electron count.
The oxidation state of radium is 0 here. Yeah, phosphine type ligand and also the alkene.
So yeah, palladium 0, D what?
Yeah, radium is D8.
Palladium 2 is D8. Palladium 0 is D10.
So then it's D10, and the number of electrons is like, it's like we have 3 L-type ligand, so it's like 16 electrons.
Okay.
So
Overall electron count is 16. Good. All right, we're going to treat this with HCl. So tell me something, palladium 0, like one of the things I like to try to build up is an intuitive understanding of just your metal, your oxidation state. Is it nucleophilic? Is it electrophilic? So tell me palladium 0, is that nucleophilic or electrophilic?
it prefers to go to palladium 2.
Okay, so that's another way of it's saying it's nucleophilic. It has an excess of electron density. And you've got H plus and Cl minus.
I can, I've never seen, but I can assume that it can oxidize H plus.
Okay.
Oxidize, reuse H plus too.
So we talked about in the oxidative addition lecture, if you think back to it, Nima, that one class of electrophiles are mineral acids. So if this were not HCl, but methyl Cl, what would you want to draw?
What was the?
If it wasn't HCl, but it was chlorobenzene or chloromethane, you would have oxidative addition. So why would you think any differently with HCl? Beautiful. And so you said that palladium wants to get in its +2 oxidation state. Now we +2. And palladium 2D8 tends to like to be square planar. So maybe we're gonna, we don't know. This is just pen and paper chemistry. So we don't know, we might lose that interaction so that it can go square planar. So now we can do the quick electron count here too. Palladium 2,
C8 and then 18 electrons.
palladium 2, D8. Let's assume that the olefin's not coordinating. I have 8 electrons and we get to 16 electrons again. Okay, and then we're going to heat it up. So we're not adding anything to the flask. We're just trying to promote a step that apparently has a high kinetic barrier at lower temperature. So what could we think might happen here?
Can we do insertion into the alkene?
Beautiful. What do you want to insert?
The hydrogen.
The hydrogen. What about the chlorine? Is that interesting at all to you? If someone in the classroom were inserting the chloride, what would you say to them? All hope is lost. Give up your career in chemistry? No, you didn't say that. But is there any fundamental problem with that?
I actually have no answer for this question. I just never seen. I personally never seen.
Well, I think that's a fair answer. It's like your experience, you don't see that elementary step, and that means that elementary step is less common. Why is it less common? It's because hydride has a higher migratory aptitude. We didn't talk about heteroatoms and where their migratory aptitude is. They're typically much lower. There's some exceptions again, but typically much lower than hydrides, than aryls, than alkyls. So they don't like to insert. Why is that? Because they tend to form stronger bonding interactions with the metals, and thus there's more of a thermodynamic penalty if they do insert. Okay, and then we said we want to insert this. So we're going to insert the hydride. We're going to form a new carbon palladium bond. And then those two new bonds we form are going to need to be cis to one another. Let's see if I can draw this in a way that doesn't look too terrible. So we're going to form cis, and then that kind of doesn't look great, but the idea is they're adding from the same phase. And then you could imagine this also might not be that happy, so it might want to react further.
If you go for like reductive elimination, I don't think palladium would be happy. But
Okay, you could reductively eliminate the carbon chlorine bond.
but then we have palladium 0, and then it's gonna be 14 electrons, right? So like not that good. So also beta carbon elimination is not here, right? Because if you have hydrogen,
Probably not. I mean, it is kind of strained, so you could convince yourself that maybe there's a strain release argument. But in having just inserted into that olefin, we now give ourselves an opportunity for to potentially see another beta CH bond. And so we don't know. I mean, again, this is all pen and paper chemistry. So maybe it stops here. If you were to think that, that would be reasonable. You'd get full points on a midterm because you don't have any additional information. Or maybe you say, okay, I'm just gonna take this one step further because I see this non-degenerate beta CH bond, and that could potentially, we're in the beta hydride elimination part of the class, so it could stand to reason that that's going to form a new olefin and eliminate that way. Yes.
For the oxidative addition product, I was counting it to be 18 electrons.
Yes, it depends on if you, I think, if you count this olefin as bonding, I counted it as not interacting. I drew this as we're not sure. we're not sure, but we know that palladium-2 generally likes to be 16 electron square planar. So I counted that as not bonding. If you count it as bonding, you'll get to 18 electrons.
But then for the migratory insertion, is it like usually you need to coordinate for all of it before you do the beta hydride elimination?
You do need to coordinate, yes, for an inner sphere mechanism. So I think whether you, how shall I explain it? So it's like this, the stable, like the observable form could be 16 electron, but it can still then coordinate the olefin, get to 18 electrons and do the downstream chemistry, even though that's not where it rests. That would be an intermediate en route to your product determining transition state. If that makes sense. So whatever, if you drew it bound, great. If you didn't draw it bound, also okay, justifiable. If you stopped here, totally reasonable based on information provided. This is an example from Vlad Illich's group at Notre Dame, who's looked at these interesting complexes. And in the context of his lab's interest in metal ligand cooperativity, so the olefin can get involved in some of these elementary steps as well. We'll talk a little bit about that in subsequent lecture. Yes.
Can I ask it's a very unintellectual question, but
My favorite kind.
why can you rule out the possibility that the alkene might just get protonated off with HCl and just isomerizes to the other alkene instead of going through this whole like palladium stuff?
Yeah, that's really interesting. So if you only observed, if you only knew you had the starting material input and then you had the product shown at the end, there's other pathways you could draw. So you could draw you're talking about a Bronsted acid mediated contra thermodynamic. Well, maybe it's probably contra thermodynamic, right? Because it's going from tetrasubstituted to disubstituted styrene element. So it would need to isomerize uphill, which it could do. Maybe you can justify like when it's bound to the metal, you get a lot of strain release by isomerizing ligand uphill. But I can just, answer your question directly is that in this case, they're actually able to isolate the intermediates. So they have more insight into what's going on behind the veil. Any other questions? Al?
Is it, I guess, possible to that the oxidative addition complex is a cationic palladium-2 complex, and being cationic can help the migratory insertion?
That's interesting. Yeah, so I think that, yeah, again, I think if you were to draw that on a midterm, that would get you full points because you would probably then, I think what you're considering drawing, if I understand you correctly, is it's like this, where you have this hydride and then it's E, I, T, and then this is plus, and then you have an outer sphere chloride. And I think that is also reasonable to consider because you have this pincer structure of the ligand that it, and there are examples in the literature where having, let's say, analogous ligands like a xanthos can force a counter anion that normally would be happy to be inner sphere to push outer sphere. I think if you thought along those lines, you would be justified in thinking that way. Yeah. Okay, another, and I think this pretty much puts a bow on it. Transmetallation. Transmetallation, we talked about already in, if you think back to the early lectures, so I won't rehash all of that. There are different forms and flavors of transmetallation. There's versions where metals swap carbogenic substituents. There's versions that have redox involved, so-called, the second line here, so-called redox transmetallations, where you transmetallate from one organometallic with a metallic form of a metal, concomitant oxidation state adjustments. And then the part that I'll linger on here is the one that's most relevant, the third, and is most relevant to catalytic cross couplings, where you have one organometallic, often a main group organometallic, and it's swapping partners with, so M1 here, think boron in the context of Suzuki coupling, and M2, think palladium. It's swapping partners with palladium, and that palladium has a halide ligand or hydroxide ligand. And remember that you need thermodynamic driving force, and that thermodynamic driving force often can be understood from the perspective of electronegativity. Carbogenic group wants to go to the more electronegative element, or equivalently, the halide, alkoxide, hydroxide wants to go to the more electropositive element. This is mechanistically complex. It's one of these things where, one of these processes in science where people were happy to, so Suzuki coupling, cross couplings came online in the 1970s, and people were happy to wave their hands about this for the better part of 40 years. It was really only in the past decade where the community has really dug into some of the details of transmetallation and started isolating intermediates, characterizing them. And so this part of the notes I've actually changed quite a bit since my early times teaching it, because there's just so much new knowledge and information that has come online, which is cool. It's kind of like we're rewriting this part of the textbook, this part of the class with every passing year. So what are some things we know, what new knowledge has come online? So in a transmetallation, let's talk about stereochemistry. So if you have an sp2 hybridized carbogenic coupling partner, so think here like your alkenyl boron that you've made by a hydroboration that you're going to bring into a Suzuki coupling for a polyene synthesis. Typically, those are stereoretentive at the carbogenic substituent. So you know this intuitively. If you have a E-configured alkenyl boron or alkenyl tin, it goes in E, it comes out E. So you know that already. For sp3 hybridized coupling partners, it is more complicated. And this, again, I think like when I learned this, it was not complicated. It was taught that this is always stereoretentive, in direct analogy to how oxidative addition is always stereoretentive in a classical inner sphere mechanism. But what has come to be appreciated as the community has gained more and more access to enantioenriched CSP3 coupling partners is that this can either be stereoretentive, as shown via the right transition state, or stereoinverted via this unusual looking open transition state that I still have a hard time totally understanding. There's some analogy here to an SN2 process, but it seems very counterintuitive to me. The electrons, it's kind of like looks like an SN2, but the electrons are pushing this way. It seems very strange. But anyway, there's evidence for this. And so just as one example, Mark Bisco's lab has used these enantioenriched secondary alkyl tin and boron reagents and found evidence for stereoinvertive transmetallation. And then there's an example from the recent literature, just a cool one. You can just take a quick peek at. So here we have copper, we've got a phosphoramidite ligand, we've got an organohalide, we've got an organoboron. It's actually a 1,1 bis boron, but don't let that scare you away. So what do you think, David? If I told you allyl electrophile, organoboron nucleophile, some late transition metal catalyst, what would you want to do?
Some type of coupling.
Some type of coupling, love it. So we're just going to cross couple here. And do you want to cross couple once or twice? I drew once, so that's probably a good hint. Cross couple once. We could convince ourselves that the second one, the boron is less, the carbon boron bond is less reactive because you've now like traded one electron withdrawing boron group for an electron donating alkyl group as the carbon is concerned. The cool thing is this creates a new stereocenter, and the stereochemical determining part of the reaction is actually transmetallation. So the metal catalyst is approaching these two inequivalent carbon boron bonds and asking which it wants to transmetallate with. And through some computational work from things from Mookie Bike's lab, they pin down this open transition state for the transmetallation step and have good experimental evidence to corroborate their computational model. So this is a real thing that the community is starting to appreciate here. Relative rates, these track with level of S hybridization, making it so transmethylation becomes faster with more S hybridization, more electron richness, and less steric encumbrance. So alkynyl transmetallate faster than alkenyl. Unhindered and alkenyl transmetallate faster than aryl. Aryl transmetallate faster than alkyl, and we know this because when we're doing Stille couplings, for example, we will have a aryl tin, but the other three ligands around tin will typically be butyl groups, for example, that transmetallate much more slowly. With the sp2 hybridized coupling partners, one of the reasons they transmetallate fast is this ability to pre-associate, because you have these fluffy pi cloud electrons that can form dative stabilizing interactions with the metal, and that pre-association allows them to transmetallate more quickly. You don't necessarily have that option when the only thing you're trying to find the metal be a sigma bond that's in an encumbered environment. So that's tin in a nutshell, and now we'll do boron in a nutshell. This too, I think the collective understanding in the field has come leaps and bounds in the past 10 years. And I'll draw attention specifically to important contributions from Scott Denmark's groups. His is not the only group that has worked on this problem. John Hartwig's groups worked on this previously, and many other giants in the field. But Scott's lab published this landmark paper effectively immediately into the textbooks. The first author of that study was Andy Thomas, one of the recent speakers that we had as part of our departmental seminar, who did a lot of this work using low temperature direct inject NMR, pinning down for the first time this pre-transmetallation intermediate that had been proposed but never directly observed. So let me walk you through that. In this Denmark paper, they described two ways to make a so-called pre-transmetallation intermediate containing this elusive palladium O boron linkage that had been proposed, not observed. One way to do it is you take a trans oxidative addition complex, palladium-2, you treat that with the corresponding boron-8 complex. Common theme in boron transmetallation is that they like to transmetallate through the 8 complex. Why is that? Because when you associate, and this is, I think, part of Scott's original interest in this, is when you associate a Lewis base with boron, it increases the nucleophilicity, it increases the HOMO coefficient on the associated aryl group. So you coordinate an anion to boron, boron becomes net negatively charged. We draw the formal charge as lying on boron, but in fact, the negative charge lies on the surrounding ligands and particularly on the aryl group. So that aryl, that ipso carbon, that migrating carbon becomes more nucleophilic upon formation of the 8 complex. So when you form the 8 complex, oops. This becomes more delta negative. And then the other way to make it is just the same idea, but the opposite series of steps. So in this case, you first preform the palladium hydroxide complex, you treat it with the simple boronic acid, and you can form the same linkage. Then they were able to obtain evidence that what happens next is one of the L-type ligands dissociates upon transfer, and I'll just push arrows so it's clear what I mean here. So this arrow group needs to transfer onto palladium, the L-type ligand needs to dissociate, and then now you're poised for your key CC bond-forming reductive elimination. There have been some cool contributions in terms of solid state characterization. One from a few years ago from the December group, who showed that if you use a special aryl boron that actually has a chelating group on it, you can dramatically slow down the rate of transmetallation, so much so that you can stop it there, isolate it, and even get a crystal structure here. So what this looks like, if we superimpose this onto the Denmark framework, is we have a aryl group that we prevent from migrating because we tether it to the ligand. And in so doing, we stop it. It still has the key palladium O boron linkage, but now we can isolate it and characterize it crystallographically. And this has even been extended to nickel in the more recent literature. Questions? Okay, now we're going to put many steps that we've learned together. And I don't normally do this, but this is actually an example from my own lab. So that makes it easier to remember what happens. This is problem of the day. If you're following problem of the day number 4 from the day 6 handout, we have this. We start with a palladium NN pi pincer complex. We treat it with sodium fluoride and aryl boronic acid, and then a series of steps, some not surprising, some surprising, happen. And probably to maximize the level of torture, I should call on somebody from my group for this. Catherine, get us started. Okay, so first we've got aryl boron plus sodium fluoride. What do we think the sodium fluoride might be doing? We don't know, but what would be a reasonable hypothesis? Fluoride associates with boron. We don't know, but this is a reasonable hypothesis. Now we're overall anionic, form the 8 complex. And then that's going to set us up to do what? Beautiful. So the 8 complex, I won't draw this, but the 8 complex will come in, displace the acetate, and now you have your palladium OB bond linkage. That will trigger transmetallation. That's going to put this aryl group here. I'll ask you for one more step, Catherine, and then so we've got a aryl palladium, we've got a bound olefin. What do we like for happening next? Migratory insertion, beautiful. So we're going to insert. This looks pretty unhappy. Here, let me draw this with defined stereochemistry. Tertiary alkyl palladium. But it is the only reasonable looking thing to draw. And then we're just gonna draw that open coordination site there. So now we kind of have a conundrum. Anybody have an idea of what might happen next? Oh, beta carbon elimination. Okay, why not beta hydride elimination, Alex?
Because there is no syn beta hydride.
Beautiful. So we have this requirement for syn, hydride to be syn. We look on the right, we only have the aryl. That's not good. And then on the left, we do have a CH here, but this looks quite precarious. Why does that look precarious? Brett's rule. If you were to eliminate it, you would make it anti-Brett olefin, which maybe you could convince yourself you could do if you're bound to a metal. There are examples of anti-Brett olefin metal complexes where the metal stabilized. But what Alex proposed was, I think, on point here. And he said, because we have a strained carbogenic ring here, maybe if I understood what you're proposing, Alex, you're saying beta carbon elimination. So that's the beta carbon. And then what will we get here?
You get the olefin between where you're already attached and the former bridgehead carbon, and then you have the main alkyl.
Is that what you had? Alex,
Sorry, what was the question?
is this what you had?
Yes.
Okay. Now it's 4 coordinates. We don't have open coordination site. And then are you happy stopping here?
I think I'm happy stopping there, because that's what's on sheet.
Now you have a pretty, so even hypothetically, if it wanted to do anything else, it's this tetradentate coordinate structure, pretty rigid. It's hard. There's a big energetic penalty for this to do anything other than just stay like this. I think in our own hands, we found that you really have to push it to do anything. If you treat with molecular iodine, for example, you can convert the carbon palladium bond to a palladium, carbon iodine bond, but not much else. Okay, very good. So this stitches together then several elementary steps: transmetallation, migratory insertion, and beta carbon elimination. And I think importantly allows us to consider a situation where we can reason through why beta hydride elimination, why other pathways wouldn't happen. Good. Any more questions? So I have sorry, let me go back. I have some additional notes on CH activation that you can look through. I won't go through these because we have some dedicated lectures later in the class to CH activation, but if you see this PDF uploaded, you'll see them there. So I didn't miss anything, just for your own reading at this point if you want to, and then we'll cover this more formally later. Okay, a few minutes left. And so we'll get as far as we can in the carbene stuff.
Last question.
Yes, please, Oliver.
Why do they use the fluoride in this case and they don't choose water?
Yeah, I think there's I mean, I can comment on it because we did it in my own lab, which is that we had a catalytic reaction that this came out of, and that catalytic reaction worked best with fluoride. So we knew that fluoride would work, and we didn't really do a lot of reoptimization. I think if you were to design this from scratch, you'd probably start out with something else first. You'd try aqueous base or something as your initial potassium phosphate, tribasic, water, and organic solvent. Some of the more common things that you would see to promote. But it is fairly common, I would say, to add fluoride, and one of the common proposals is to populate that formation of that 8 complex. So it's not outside of the realm of what people would think about. All right, metal carbenes. Quite a bit to unpack here, and I'll try to get through kind of the primer version of this, and then we'll take a little bit more of a deep dive into the next class. Carbenes, the distinction I'd like to draw before jumping into metal carbenes here compared to most of the other ligands that we've covered are when you dissociate that ligand from the metal, it's stable. We say, and we dissociate it, we get to the closed shell state, and that is a stable entity. And that is not normally true. Of course, there's no exceptions, not normally true with carbenes. We know, so now don't think about metal, just think about what you know about carbenes. We know that they come in 2 forms. So maybe I'll step back. We know that carbenes are divalent carbon. Carbon is sp2 hybridized with 2 substituents and 1 non-bonding sp2 orbital, and then the orthogonal p orbital. In terms of electron occupancy, the sp2 orbital can have effectively a lone pair, or the p orbital can have 1 electron and the sp2 hybridized orbital can have an electron. And those define the singlet and triplet state respectively. The triplet state can actually exist in 2 forms, a linear and bent form. What I've drawn here is the bent form. And typically the triplet, again, this is all things you've probably encountered before, the triplet is more stable, and that goes back to Hund's rule. And it's stable to the tune of 8 kcals per mole. The exceptions to this are when the R1 or R2 groups have heteroatoms. And we know that these engage in reactions, like if you have a carbene and you have it in the presence of an olefin, it will undergo cyclopropionation. And we know that the stereochemical outcome of that cyclopropionation allows you to read out the character of the carbene. This is a relatively new branch of organometallic chemistry in that it only dates back to about the 1960s, where the structure and bonding of metallocarbenes was first elucidated and understood. So there's a couple different layers to this. The first has to do with categorization and then electron counting. So from the perspective of the electron counting and broad strokes categorization, there are 2 types: Fisher type, Schrock type. Fisher type shown on the left, Schrock type shown on the right. Fisher type, typically, these are late transition metals getting into the middle of the periodic table, typically in low oxidation state, and often a diagnostic feature of the Fisher type carbene is that you have a heteroatom bonded to the carbene carbon. The consequence of this are that these, what I have drawn here is a metal carbon double bond, can alternatively be viewed as a dative bond, and that bond between metal and carbon is relatively weak and relatively long. Then on the opposite extreme, everything is flipped. You have the Schrock type carbene, early transition metal to middle of the periodic table. The groups that are typically on R1 and R2 are alkyl or H. If it's alkyl, it's called an alkylidine. If it's H, it's called a methylidine. And then because of one way to think, I think the easiest way to think about this is just the electronegativities of the metals dictate how the metal carbon bond is polarized. So for a Schrock type carbene, where you have a more electropositive metal, the polarization, the dipole moment, so to speak, is such that the metal is electropositive and the carbon is electronegative. You can think of this as like a 1-1 anion bounded to a metal, and then the opposite is true. You have a more electronegative metal that is competing harder for electron density, and this starts to then look more like a carbonyl type bonding interaction. So those are the two, and so the Fisher type, we're going to count the carbene as a L-type ligand, Schrock type, we're going to count it as an X2 type ligand. That's the upshot of what I'll tell you in a moment. And then now we'll zero in on some other subtypes, and all of these, in terms of electron counting, generally are, here, all of these in this category are Fisher for the most part in terms of electron counting. There are carbenoids. Carbenoids are a weird, ill-defined type of metal organometallic species that has free carbene-like reactivity, and the bonding depiction is sometimes a little bit hard to understand. We encounter carbenoids if you've ever seen reactions where you take a diazo and you treat it with a late transition metal like these ruthenium carboxylate, tetracarboxylate dimers, or other late transition metals, polydentate ligated ruthenium, rhodium, copper. These go through carbenoid pathways, and we'll see a manifestation of that in one of the later problems of the day. There is a interesting subtype called vinylidines. Vinylidines are generated spontaneously. They're kind of like, you know, they're these weird metalloalline looking things. They're generated spontaneously when you treat a terminal alkyne with a late transition metal. The H atom slides over to the to this carbon, and then you form a carbon metal double bond. And because the vinylidine species have a singlet ground state in the free form, these are treated like Fisher type carbenes in terms of the electron counting. Then you have N-heterocyclic carbenes, which, remember we said Fisher carbenes, one of the diagnostic features is they have a heteroatom. In the Crabtree textbook, they describe N-heterocyclic carbenes as Fisher carbenes on steroids because you have two heteroatoms. And so these start to, in terms of their frontier orbitals, start to look more like phosphines and ordinate and engage in electron counting, or you electron count them similar to phosphine. So if it's ever confusing to you, you see an NHC, just think, I'm going to electron count this as if it was a phosphine. Okay, let's, we'll take each section then in a little bit more detail. So first, Fisher carbenes. We said that in Fisher carbenes, the metal is is more delta minus, the carbon is delta plus, and overall electrophilic. Here's what the frontier, here's what an MO cartoon depiction looks like. So remember, you have in a Fisher carbene, it is a singlet form of the carbene. So the sp2 hybridized orbital is doubly occupied, and that's forming a bonding interaction with a d orbital of the metal. And then a filled d orbital on the metal of appropriate symmetry is forming a back bonding interaction to the unoccupied p orbital. And then because you have these heteroatom substituents here that have lone pairs, it's not always a heteroatom. Sometimes a phenyl group through conjugation can also provide some electron density. You're getting stabilization into this unoccupied p orbital. So how do these react with other chemical entities? Nucleophiles will attack at carbon because of how the carbon metal bond is polarized. Electrophiles will engage the metal. We talked about often Fisher carbenes are late transition metals in low oxidation state. Tend to see these with 18 electron coordinatively saturated complex D6, and we'll see how this contrasts with the Schrock type carbene. And then in terms of the other ligands on the metal, because the metal tends to be this more low valent, more electron rich type of metal, the overall complex is more stabilized when the other ligands are pi accepting. So you often will see carbonyls on, but not always, of course. And then on the carbene side, it's stabilized when you have heteroatoms that can engage in pi donating interactions through their lone pairs. Carbon metal bond in this case is relatively weak. It can be, you can denote, and in the old literature, people did denote these bonding interactions more like this in the dative form to signify that it's relatively weak, that it's L-type. And then the Schrock type carbene, again, we have just effectively the opposite situation. So now the carbene component in the MO depiction, we're treating like a triplet. It has a singly occupied sp orbital and a singly occupied p orbital. And those are forming bonding interactions with d orbitals of appropriate symmetry that are each singly occupied on the metal. The metal carbon bond is polarized in an opposite way. So now it's nucleophilic at carbon, and other electrophilic chemical entities will engage at carbon, and it is electrophilic at the metal and is Lewis acidic. And this I think is intuitive when you recognize that these are often 14, 16 electron metals in high oxidation state, typically D0 or D2. We saw an example of a Schrock type carbene in an earlier problem of the day that I think Alex helped us get through as it pertains to alpha elimination. And then in terms of the other ligands on the metal, this is often stabilized because the metal is electron poor, high oxidation state. The more strong sigma donors you can coordinate around it, the better in terms of stabilization. And in this case, if you were to have a heteroatom on the R1 or R2 groups, this is destabilizing. And I think that's intuitive if you just draw this out, run this thought experiment. What if you had a heteroatom here that had a lone pair? Well, then immediately you're going to have a problem because that lone pair is going to be trying to donate electron density into an already partially filled orbital. So the carbene, the R1 and R2 groups typically tend to just be H or alkyl or sometimes aryl. And then the bond has more double bond character, stronger, shorter. And then in electron counting, we just count this as a 1,1 bis alkyl anion, i.e. an X2 type ligand. Okay, and then the last thing I'll just leave you on, so I can introduce chemist of the day from day 8, who hails from the great state of Alabama, as was pointed out by, or at least has spent part of his career in the great state of Alabama, pointed out by Sebastian. So NHCs, what is special about NHCs? These are generally spectator ligands in catalysis. We can tune the properties of the NHCs just like we do with phosphines to make them more super bulky or more electron donating. They tend to be very strong sigma donors. The extent to which they can engage in pi accepting has been debated, but they're now pretty widely agreed on to be weak pi acceptors. And I think the distinction here is that unlike your Fischer or typical Fischer or Schrock type carbenes, and heterocyclic carbenes can also exist stably in the free form. So that brings us to chemist of the day for day 8, who is, I don't know if anybody might recognize the chemistry, even if you don't recognize the photo. Alex, you look tempted to take a stab.
His first name started with a K.
No.
I'll take a stab.
Anthony or Duenga, thank you. Is that Wenji? Wenji, congratulations, you get a starburst. Who spent his career across several different institutes, DuPont. The work that we'll describe here is from DuPont, but he also spent time at Alabama, Roll Tide, now is at Georgia Tech. Duenga synthesized the first, or one of the first, along with parallel work from our neighbor Guy Bertrand, the first persistent carbene now, that now bears his name. There's called Arduino or Wanslick type carbenes. And I've actually made one of these myself. It's kind of an odd story. So these are singlet. So we in their ground state, stable, monomeric. This made a big splash and has continued to reverberate in the community. And the key is this 1-1 heteroatom die substitution, as well as the 5-membered ring structure that leads to the stability, enhanced stability of these types of carbenes. So problem of the day 1 from day 8 worksheet asks you how you would go about synthesizing such a thing. So I know a lot of folks come from a synthetic background. So Alex, give me a thought here about how you'd make this.
I think you can take the adamantylamine, glyoxal, and formaldehyde or paraformaldehyde, cook it up, and that gives you the cation, and then you deprotonate it to give the carbene.
Okay, so let me just do I know this is almost such a simple molecule, it's almost silly to do, but I do think it's worth thinking like Alex's retrosynthesis. The key point is you do not want to try to make this an adamantyl bond because it's super hindered. So you want to bring in adamantylamine. And once you've made that decision, everything else falls into place. So your building blocks are going to be, and then what order you put them together. So and I think you said also you're going to treat with base. So often for NHCs, the starting material are these imidazolium salts. That's true here too. And then you have an X type. And then treat with base. We want to get the adamantylamine out of this. So we're going to get to adamantylamine, and then I think you said glyoxal and formaldehyde or some C1 equivalent in the formaldehyde, or it needs to be in the formic acid oxidation state, right?
I don't think so. I thought so initially too, but I think if you draw the condensations and push the arrows surprisingly enough, it looks like it needs to be in the formic acid oxidation state, but it's actually formaldehyde.
Okay, so these are effectively I see what you mean. Yeah, so these are effectively your building blocks, at least in terms of oxidation state. And then you can talk about what the actual preferred components are, and you can find that in this Arduino reference if you want to hear more about that. But then the other way to make it alternatively, like if you have an N, instead of an adamantyl group, you have an aneryl group or some bond you believe you can make, then you can do this in a different sequence of events and form that CN bond later. And then you can get back to 1,2-diamine type starting materials. Okay, so we'll leave things off there, which I think is a good, and you can think through problem of the day number 2. We'll start off next time with this, which is just a kind of thought experiment exercise of, based on what we've learned so far, which different, what the pKa's of these CH bonds are. So we'll pick things up there. And, see you all on Tuesday. Stay after for a minute if there are any questions. Thanks, everybody.